Dear viewers, welcome to the lecture series in biophysics. Today we are going to learn about the three-dimensional molecular structure determination using single crystal X-ray diffraction. If you remember, in one of my presentations you have learned how direct methods could be used to determine the three atomic position of an atom constituting a molecule. In today's lecture we are going to see in detail a suite of programs called SHELXs programs, which has been written by Professor George Sheldrick from Germany. SHELXs program has two programs. One is called SHELXs S. S means structure determination. Another is known as SHELXs L. L means least squares refinement. So, we are going to see in detail both the programs. If you remember, we have earlier learned that a molecule is made up of atoms of different species like carbon, nitrogen, oxygens and hydrogens also. These atoms contain electrons, and since it is a crystal, these molecules have a three-dimensional periodicity and lie in three-dimensional planes. When X-rays are incident on these planes called Bragg planes, and interaction happens between the atoms, in particular the electrons in the atoms and the X-rays, because of which X-rays are diffracted. So, these diffracted rays can be photographed in the 50s or 40s, but nowadays using electronic detectors the intensities can be captured. So, the experimental information that comes is only Bragg intensities. Here we keep a crystal of dimension 0.2 millimeter length, breadth and thickness in an X-ray beam, and we have automatic diffractometers costing crores of rupees. You can collect data within an hour 45 minutes to see whether a molecule is there in the crystal or not. Here the principle is atom is located wherever electron density concentration is maximum. As you see this equation, which is called a Fourier synthesis, electron density at any point x comma y comma z equals 1 by V, volume of the unit cell. It is a triple summation over the Miller indices H, K and L. The coefficients in the Fourier synthesis are not only the structure factor amplitude of Bragg reflection you are getting from experiment by taking square root of the measured intensities, but also the phase angle of each Bragg reflection, which is not coming from the X-ray diffraction. This is known as the bottleneck called phase problem in crystallography, for which an elegant answer had been given by Professors Karl and Hoffman in early 50s, but they had assumed some points which have been not accepted by the physicists as they are against the laws of physics. Namely, a crystal with continuous electron density can be replaced by idealized one made up of non-vibrating point atoms. According to solid state physics, atoms cannot be ideal, they cannot be at rest, they have to vibrate. So, in that case how can you say non-vibrating? Other thing is, atoms are really spherical atoms, the electron density, because electrons are not rest, they are moving around an atom, and roughly the center of electron density cloud we take it as the atomic site. So, when being so, how can you assume the spherical atom shape atom as a point atom? So, these are the objections, for which both the professors have given an answer that what they are going to propose finally is a set of coordinates for each atom, 3 coordinates, which are only approximate. Then they can go to reality by considering spherical atom and assuming thermal vibration. But even then, just because one person belongs to mathematics and another person belongs to chemistry, these physicists do not accept. The battle went on, and finally in 1966 the wife of Professor Jerome Karl, namely Isabella Karl, proved in a dipeptide how this method called direct methods worked out and got the answer. Thereafter thousands of molecular structures have been determined using this method, direct method, meaning directly from measured intensities we can get the three-dimensional structure. In 1985 more than 30 to 40,000 structures determined. So, as a waiver, a mathematician also received the Nobel Prize, and Nobel Prize was shared by Professors Karl and Hoffman in the field of chemistry. So, this is the history of this methods and what is the phase problem, everything. So, as we already know, once you know the unit cell parameters A, B, C, alpha and beta and gamma, the volume is known. This comes from experiment by taking square root of the measured intensities, and alpha is the unknown called phase associated with the structure factor, which is coming from the direct methods. So, as I told you, this is explains the phase problem. In order to compute atomic site, one has to calculate the electron density at various points in the unit cell and the maxima give atomic location or site, because only atomic sites we have electron density distribution, at non-atomic site no electron density will be 0. But due to theoretical limitation and experimental errors, we do have some small values for that. But to compute the electron density, one has to know not only the structure factor magnitudes obtainable from experiments called structure factor amplitude of Bragg reflection HKL, but also the phases alpha of HKL which are not available from experimental measurement. This bottleneck is called phase problem in crystallography, which has to be overcome if you want to do the Fourier synthesis to calculate electron density and also the electron density maximum to locate the atomic site. And these direct methods are the mathematical methods involving probabilistic methods, which approximate only, using which phase information could be obtained directly from the measured intensities. It never signifies directly, means very simple, no complicated mathematics are there. Here the probable values of some linear combinations of phases called structure invariants and structure semi invariants are first determined. Then using that, the individual values of the phases which are going to be used in the Fourier synthesis for this Bragg reflection HKL are obtained using tangent formula. As I told in the beginning, these are the assumptions made by these pioneers for the easier mathematics. The unit cell is supposed to consist of n non-vibrating point atoms, because there is nothing called point atoms. If there is point atom, how will you discriminate between a chlorine, nitrogen, oxygen and hydrogen? So, that is the objection. Second objection, non-vibrating atoms do undergo vibration. How can you assume this is a thing? These two are assumed for the easier mathematics only. Later on, this can be adjusted by giving or going to reality. You can assume atoms to be vibrating, and we can assume to be atoms to be spherical atoms. And the electron density is assumed to be everywhere positive. For again, for easier simplification, there should be a random distribution of equal atoms. For point atoms, this structure factor mod f HKL cannot be used, because mod f HKL corresponds to spherical atom, and the structure factor amplitude corresponding point atom is modulus E HKL. This is known as normalized structure factor amplitude. Whenever you put a signal modulus symbol, is called amplitude. From these measured intensities or mod f HKL square, you can get square of the normalized structure factor by using this equation. This epsilon is a constant depending upon the parity of the reflection. Fj is the atomic scattering factor. Here you have to take into account the thermal vibration also. Capital N is the total number of atoms in the unit cell. Since it is a probabilistic estimate, the estimate will become poor as the number of atoms in the unit cell becomes large. So, this I will tell you when you talk about the formula. Therefore, the direct methods which are traditionally useful to small molecules, say let us say the present technology, even up to less than 200 atoms in a molecule can be routinely solved. But when these methods are applied as such to solve macromolecular structures consist of thousands of atoms, these methods fail, because direct methods work only at atomic resolution data, and not only that, the total number of atoms should be less than 200 or 100. Now, what are the various steps involved in such a determination procedure? Once you have the good crystal without any crack or clusters of crystals, this crystal, after checking, if you have a dimension of 0.2 millimeter in all the three directions, then you can take it to a diffractometer, mount the crystal, and you can get unit cell parameters depending upon the systematic absence of certain reflection. The machine will assign what is the space group, everything it will give. Then this data reduction means you are subtracting the background from the peak area, is called reduced data. We have to find what is the overall thermal factor of atoms, that is determined by graphically by a procedure known as Wilson's plot. After that, this thermal vibration is incorporated in the atomic scattering factor and E values are calculated. Then these E values are sorted from larger to smaller, because direct method the probability of success in the structure invariance becomes more and more if the product of the 3 E values selected for the triplets are more and more. That is why we use strong E values to select the invariance. So, to select the invariance, what you do is you do a convergence procedure. You take 2 or 3 reflections and assign phases if they are non-centrosymmetric crystal, or assign symbols plus or minus if they are centrosymmetric. Usually you take 4 reflections. For the inertium of fixing, we will take 1 more reflection. Generally we used to take 5 reflections and assume their phases or signs to be known. Based on these 5 reflections, phases or signs, the entire remaining 495 reflections that are going to be used in the E map are going to be assigned. So, in the convergence procedure, to select those reflections, we have a broad spectrum of the triplets, and you select only those reflections which are occurring more frequently in the triplet relation. Then you take those reflections and assign them as origin defining reflections, for which their phases or signs if they are centrosymmetric are known. So, from this starting phases or signs to be known, I can get the phases and signs of other 495 reflections from the knowledge of these 5 reflections, and that is known as divergence. From a small set in the start, you are diverging, get a larger set of phase, right. Here from a larger set you are doing convergence and select what are all the reflections which are mostly linked in the triplet. Finally, as I told you that if you take 5 reflections and each reflection has 2 choices in the phases or your symbols, totally you have 2 power 5 sets in the origin, 32 sets. So, each set will give you a solution, which set is the best. That is done by doing a figure of merit calculation, and usually there are so many ways of determining figure of merit, and there is a term called combined figure of merit. In the package we are going to detail the SHELX package. The best set is the one which has the smallest value for the combined figure of merit. Only for this set, E map is just like a Fourier map, in which instead of the structure factor a mod f, we are using mod E, nominal structure factor, and that is done for the correct set. So, this already we have seen. So, this it is not an instruction file. The program name is SHELX. S means structure solution program. So, these are the input, title, cell. First is the wavelength used, maybe copper K alpha, this is molybdenum K alpha. If it is copper K alpha is 1.5418 wavelength. Then A, B, C unit cell dimension in angstrom, alpha, beta, gamma in degrees. Here the title can give anything, starting date or compound name or space group, everything for reference only. Here you have to read it as Z-R. Okay. Z means total number of molecules in the unit cell. Error means standard deviation of A, B, C, alpha, beta, gamma. Then lattice, if it is non-centrosymmetric lattice, then you got to put a minus here. If it is centrosymmetric, do not put any symbol, and if it is primitive lattice, you got to give a number 1. Each type of lattices has a number. Symmetry position, there is always an atom at a parent atom at x, y, z. In addition to the parent molecule, if you have other molecule related to the parent by a symmetry, what is the symmetry? So, that is given as this position. Then what are all the scatterers present? Carbon, hydrogen, nitrogen, oxygen. In each of the scatterer, how many atoms are there in the unit cell? So, here you have to be very careful. 52 means carbon there are 52, 60 means hydrogen there are 60 atoms, nitrogen there are 12 atoms, oxygen there are 4 atoms. You have every freedom to put oxygen here, but it has to go along with 4. Okay. If there is something wrong here, your calculated structure factor will not be correct, wrongly calculated, and R factor will be wrong. Truff means tangent refinement, the phases are obtained using tangent formula. HKL F4 means your intensity data collected is of the form Bragg reflection HKL, intensity standard deviation, this is the end. the program expects another file known as .hkl file. If the previous file name is x.hkl, this x.ins instruction, this you have to give it as x.hkl. These are the brag reflections, integers including positive or negative values and also 0. This is the intensities, standard deviation of intensities. Automatically this come from there. Whenever you collect data, no, the charge coupled device machines you use, the output will be this. They will be giving this. Even if you do outsourcing, they will give the instruction file and also your reflection file. The end of the reflection is indicated to the computer by typing 0 0 0 everywhere. Now, the chemist knows the formula. Okay, even if it does not give you the formula, you can get the structure no problem by looking at the bond length, single bond, double bond and so on. So, he has given me the tentative structure he expects. So, ring atom everywhere the C is there, methyl means CH3, then C nitrogen. Okay. If you count the total number of atoms here, 6, 7, non-hydrogen 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 atoms are there. So, your aim must be to get the 3 positions each for these 17 atoms. So, now I ran a program SHELXs 97. 97 is the year in which it is released. So, this is a crystal structure solution. These programs are packed in a suite called WinGX. Okay? WinGX, all the crystallography programs needed are distributed freely only, but I cannot distribute, we can get it. And this is a copyright SHELXs program, where first it is written in 1986 it was released. Now, it prints out whatever you are given the instruction. Okay. Then here TPR means triplet. This is a structure invariant, a sum of 3 phases phi of reflection H plus phi of reflection K plus phi of reflection L will be probably 0 provided H plus K plus L are exactly 0. When it says reflection H, K, L, by H I mean 3 integers H1, K1, L1, by K I means another integer H2, K2, L2, by L I mean another integer H3, K3, L3. By telling the structure invariant definition as H plus K plus L equal to 0, I mean all the H's to be adding to 0, all the K's to be added to 0, all the L's should add to 0, which means that by H plus K plus L is identically 0, I mean 3 equations simultaneously obeyed. One is H1 plus H2 plus H3 has to be 0, K1 plus K2 plus K3 has to be 0, and L1 plus L2 plus L3 has to be 0. Now, the program has used 4014 triplets, because these triplets are used in getting the individual phases using tangent formula, and this also I will tell you later. There is another 4 phase invariant known as quartet, and this quartet can give the phase sum which is equal to plus or minus pi, and since that cos of pi is minus 1, we call it a negative quartet. So, it has used 2340 negative quartets. These triplets and quarters are called 3 phase structure invariants and 4 phase structure invariants. They are used in the field of direct methods. Now, if you look at this end, it is telling map name is E values. So, what you have done is not a Fourier map, E map, because direct methods assumes point atoms, you have converted mod F into mod E, and that only you use. We use only strong E values, 786 values have been used, and here they are given the cutoff. Minimum E value selected for generating the triplet is 1.2, maximum is 5.0. So, that is all. So, based on these direct methods, it has given positions of 17 atoms. See, so it is already run program within 1 second. Within a second, it has given the position of 17 atoms. The Professor SHELXs has to be congratulated, because all the direct methods results he has elegantly packed into this program SHELXs. This even in the global level, this is the only program which is running and getting the structure within the shortest span of time. So, this took in 1950s 1 year to solve, because no computation, no electronic devices to measure the intensities, calculators are not available, and how to do a Fourier map, everything they did by intuition and hard work. Now, for this trial model, it is giving an R factor reliability index as 22.2 2%. I will tell you later what I mean by that. Now, this is called RES file. So, result file, the program produces 2 files, you are giving 2 inputs, star can be any name you can give, star dot ins instruction file and star dot hkl. This program will give you star dot res result file and star dot lst file, list file. If you are very much interested in learning the crystallography, you got to go through the second file, lst file, to look at the various stages of that. Okay. Now, first thing, let us go one by one. The last column denotes the electron density of each atom. So, the program does not know what is carbon atom and what is, which is nitrogen, which is oxygen, does not know, but it has assumed all the atoms to be of equal type, species 1 is carbon. So, that is called equal atom structure, because without having some scattering factor value we cannot calculate Sachar factor. If you look at the definition of Sachar factor, earlier we can define f of hkl equal to summation j equal to 1 to n little fj atomic scattering factor e power 2 pi I hxj plus koj plus lzj. So, for fj calculation we need some species. Here it assume the molecule are made up of same species of atoms, species 1 which is carbon. Okay, that is fine. Later on we are going to identify species. 3 positions it has found x, y, z for one atom, second atom, like that. In this program, whichever parameter we do not want to adjust or refine from the second stage, you can add 10 with that, which means that this is a parameter where I have added 10. So, the actual value was 1, which I do not want to be adjusted. This 1 is nothing but occupancy. Now, an atom 60% of the time it can be in one position, 40% of the time it can be occupy another position. If that is the case, for this Q1 we will have 2 positions, one with occupancy 0.6 and another with occupancy 0.4. Total occupancy of each atom when they have 2 positions should not exceed 1. Sometimes we refine the occupancy, refine means adjustment of the parameter. Now, the program is ready for refinement. So, the adjusting the positions and the thermal parameters slightly to get a better fit between the Sachar factor you are going to calculate out of this structure and the Sachar factor amplitude you already have from your experimental data. Now, so this is what they are telling. I will give approximate position, go to reality by assuming physical atom and also thermal vibration. Now, if you look at the last column, here the species are carbon, nitrogen, oxygen only. The difference is only 1 electron, 1 atomic number means. You see here, gradually, slowly they decrease. When it is 17 to 122, suddenly it goes to double digit 56 only, which means some strange thing is there, which means you got the structure up to whatever atoms you need, everything is pakka, right, behaving properly. These are called spurious peaks. We can delete these peaks. There is a program called Platon, it is a free program, where this, when you invoke Platon from the RES result, a plot is given with all the Q's. Already you know that beyond 17 they do not belong to the molecule. So, we can delete them and have a clear picture, right. If you look at the structure given by a chemist, I have this ring, the methyl group carbon is here, is a nitrogen, X, hydrogen I will fix later, carbon, oxygen here fine, CN is here, then CN, CH3. So, by looking at the figure, you can identify among the Q which species are carbon, which are nitrogen, which are oxygens. Even if the chemist does not give me a picture, by looking at this length, this will be shorter, C double bond O will be shorter than C single bond C. We can guess whether it is double bond, single bond, whether it is nitrogen or oxygen. It will be, but you can get an answer. So, now what I am going to do, having known this structure given by the chemist, I can assign the species, right. So, as I told you, in crystallographic convention, carbons are shaded black, nitrogens are shaded blue and oxygens are shaded red. So, the moment you change the species name as O, C or N, automatically the color changes happen and the instruction file, the species are automatically renamed. See, previously it was Q only, now the moment put C it is 1, the moment you put N nitrogen it goes here 1, 2, 3, nitrogen third species it has put 3, you did not type anything, there is a connection between the plot, graphical plot and the instruction file. Oxygen is fourth species, 1, 2, 3, 4, this is okay. So, this is known as species identifier. According to this number, it finds what is the species and takes the corresponding atomic scattering factor value. Atomic scattering factor of each atom is not a constant and it varies with respect to sin theta over lambda. So, for calculating such a factor, we need Fj at different values of sin theta over lambda, because different HKLs will have different sin theta over lambda. So, your such a factor calculation, that is called mod Fc of a Bragg reflection, needs the atomic species identifier. Then coordinates are there. I am not going to change the occupancy, because already each atom has come with full occupancy 1. Now, thermal factor I am assuming 0.05. I am giving equal values for all the atoms. This is known as isotropic. Iso means same. Now, I am going to run a program called SHELXs. So, here I want to do the least square refinement. How many cycles? 10 cycles. Okay. Do you want to find any extra peaks? Yes, if they are there. How many atoms you want to find? Extra 20. Then what type of Fourier map you want to run? F map 2 means it is called a difference Fourier. It is always better to run a difference Fourier to check whether there is extra atom or not. In the Fourier coefficient, the difference Fourier coefficient will be modulus Fo minus modulus Fc. Mod Fo comes from our experiment, all the 17 atoms. Suppose you have found lesser atoms than 17, mod Fc will not be equal to mod Fo, and that difference is contributed by the rest of the atom which you have to find, and those atoms will appear. That is the use of difference Fourier. So, this is the output of the least square program called SHELXs. Okay. Here what you have to see, how many reflections are there. It will give you 2 R factors. This final R factor is here R1. Every cycle it gives the R factor known as WR2. This is known as weighted R factor. We will deal about R factors later. Usually the WR2 will be thrice that of R1. So, do not confuse. What you are going to see now is the output of the least square refinement program. The program name is, as I told you in the beginning, SHELXs 97. L means least square refinement. It is known as isotropic refinement. Iso means same. Every atom we are assuming same thermal factor in the 3 directions x, y and z. Here if you just see, we talk about 2 types of R factors. One is known as your WR2 and the second one is known as R1. This R1 is always final R factor and your WR2 is printed every cycles. Every cycle I have the value, let us say it starts from 59.4, 48.4, 45. Finally, we just see between 2 cycles no, there is something called mean shift by ESD, right, 0.001 is more or less 0 and the shift is only 0. So, between one cycle of refinement and another cycle of refinement, if there is no shift, it means you have reached convergence, right. So, another parameter you look here is goof, is called goodness of fit. Finally, it has to be as close to 1, but now it has started with 5.313, it has come down to 3.181. You have defined 10 cycles, but look at the R value, R1 is 15.8%. Here this R factor is based on 2242 reflections and these reflections have the intensities greater than twice the standard deviation or mod Fo greater than 4 times your sigma of f. But if you use all data in the R factor calculation, R factor will be little bit higher, it is 18.1, number of reflections will be 3022, because you are giving a cutoff here, your strong reflection you are considered. Now, this is called your difference Fourier output. The highest peak extra atom I am getting is 1.13. Usually hydrogen atoms will have electron density 1. So, slowly we are getting hydrogen atoms here, that is all. Here also if you look at time taken is only 2 seconds. Such a determination it took 1 second CPU, now it has taken 2 second CPU. So, this is known as isotropic refinement. And if you look at the your RES output file, everything is here. there will be slight change of this position from the input whatever given, and this is your starting value 0.05, right. So, now if you just see your structures, even though I gave 0.05, after refinement these values have come either below 0.05 or above 0.05. These positions, as I shown you, slightly different from your earlier position, that is known as adjustment of positions to get a better R factor. Now, it is using a weighting factor and also a scale factor. FR means scale, every cycle of adjustment this value will be different and this value will be different. You look at this, these are called thermal factors. Depending upon the position of the atom, if it is end atoms, vibrations will be more, thermal factor will be more. If it is the ring atom, vibration will be less, because this atom is not free to vibrate, because it is bound with C6, N7 and C2. So, let us close with this and we will continue later. We will again start with isotropic, we will go to anisotropic refinement and so on. Thank you.